interpretation of a made analysis. I used the example we made in the exercise, this suspension part of a tank. I made it out of iron cast G60. I have an axe where it's taken or pulled with 20,000 Newton, and then it turns around an axis. It's fixed in the screws. Because the screws are also on the traction, I fixed there, and here you see where it's going, turning around. 20,000 I distribute on this and this surface, each time 10,000 Newton. Here you see the model. In the model, these loads are respectively the constraints are given there. They have a bearing constraint of 10,000 Newton on this surface in the direction -z, and I put it just on the surface. That's a possible contact with the axe. The axle is put in there, and also on this side I put 10,000 newtons. So these are the two cylindrical surfaces used, as I mentioned. Because I'm pulling on one side, there is also traction on the screw, so I fixed the whole of the screws. Then the rotation acts on one side. I use the pin constraint, on the other a cylindrical constraint, which I let free in rotating and in axial translation. It's a little bit misunderstanding axial growth, but it's axial translating. The meshing, I just did it, as you see, with quite small elements. I'm looking at the elements in a sense of information. I see there are 750,000 elements. No notes, elements are 370,000 made out of material cast G60. That's in the database. Almost, I looking in Google for this iron cast G60. I find a page where I see tensile strength will be possible 280 megapascals as the RP02 value. So with a security factor of 2, I accept just 140 megapascal. I go and look at the element, and as you see, it's quite a good curvature based mesh that you see. Going back to the simulation file, I made already the analysis because it's working quite some 2-3 minutes also on my machine. As you see, there is the cylindrical constraint, the bearings, and here over there you see the fixation with the screws. So that's the deformation. A lot of elements, so I make them invisible. It's much nicer to understand this picture. If I make an animation on the full cycle, you see deformation will go up and down. That's like I supposed that the behavior will be. It's not really clear if it's turning around or not in this visualization. That's the reason I put on the elements. So I go back and say all the elements are visible. I see once more the elements. I turn a little bit and I will go back to the film, and if you look at the film you see really clearly that now every node in the cylinder is turning around the center of the axe. I go back, I don't need these elements anymore, and I see the largest displacement is 9/10 of a millimeter just on this side. It's bizarre on the other side, it's a little bit less. The reason is it's not a symmetrical part, and I put on each branch 10,000 Newton. I go and measure on one side 9/10 of a millimeter, on the other side 7.5 of a millimeter, so you see about 20% less. I look at the stress, I see the largest stress is around 170 megapascal. I said I will accept about 140 megapascal. It's a little bit better to change the scale. I put the scale from 0 to 140. What's not nice now, the scale, it has a distance of quite a bizarre number, so I put up the levels. If it's 140 levels, so I have each time 10 changing. So if I put banded, you see the bands show a quite good image from one element to the other. It's about at the same area, just a nice line. So the convergence is also in this area where it's the large stress changing quite good, but you see the large stress is not just there, just the annotation of the maximum, and you see where it was fixed totally rigid, the screws, there is the large stress, is a singularity of stress. 170 is the maximum. If I change to the possibility to include the averaging at the nodes, this 140, they go down to 164 about, so also this shows a real good convergence. Also, if this maximum level is at the area where it doesn't is realistic because it's too rigid, I just measure in these areas. I find up and also on the underside just about the same level of maximum stresses. I can make a slicing, so you have seen up there on this icon you put, and then you see inside and you see the depths of the stress value. In the cutting plane options, just turn on show preview, and then you can change, and you see you're walking through your model. Did you mention before that it's a hollow model? I'm not sure. We can measure over the thickness, so you see on top on the surface it's 87, a little bit down there it's already less than the half. Also inner side you have a large stress, it's 80, so also everywhere I'm measuring it's about 60 to 80 megapascal. As a conclusion, you can say in this case the dimensioning of this part is really acceptable. Just think about that you put on show preview, and then you can walk through the part. You can change also the direction of your cutting plane. You say just the normal of the cutting plane, as an example said, and it's cutting in a plane XY, that's the plane perpendicular to Z. So also here you have seen inside, outside. We are changing to the Y direction, and then the cut will be from this side, so back there. That are the main possibilities how this cutting is working. Think about that. Show preview will be active. I found here also some maximum inside of the cylindrical surface. It's a kind of a singularity because it's really a rectangular angle. When I turn off this cutting plane and I see outside, I'm really happy about this simulation. So that's all you learned.